All right, well, good morning, everybody. So I started the recording. So on your own, at the end of class on week 3, you should have learned a little bit about the real basics of probability, just some simple definitions and how to compute some very basic probabilities and then some probabilities from tables. So this week, what we're going to do is we're going to expand on that, and I'm going to do all the advanced rules of probability with you. And then on your own this week, under the week 4 tab, the post-class requirement, I have another lecture here on probability. This is just like kind of a review lecture of just some of the harder problems in probability. So it's worth a watch. I think it's like 12 minutes. It's shorter. It just handles the harder problems that I do in class today. And then on your own, you're going to be learning about something called discrete random variables. And then under this one here, you're going to be learning about something called the binomial probability distribution. Those are a little bit harder concepts. So this week, instead of a online quiz, I have this PDF file. So it's 9 problems. So what you'll do is you'll download it and you'll print it out and you'll write in your solutions. And then what you'll do is you'll scan your results, or you can take pictures of your work and submit it through this tab. So what you'll do is you'll click this week 4 assignment. You'll scroll down to browse my computer. You'll attach the file that you have, wherever you saved it, and then you'll just hit submit. Also, to help you on the homework this week, the homework is 9 questions. I have a third-party video on almost all the questions here that show you how to do it. If you're interested, this is another way to do the homework. Yes, I'm going to grade it. Yep. I'll take a look at your answers and I'll grade them. So it'll take me a little bit of time to grade it by hand, so you won't get the results immediately. Okay. Does anybody have any questions about that for this week? So at least in terms of the probability questions this week, all the probability stuff I'm going to cover in class, and after class you'll be able to answer all the probability questions. And then the last few homework questions, looks like questions 7, 8, and 9 are all covered in my post-class lectures. Sound good? I'll take, all right, thank you. So under week 4, I just posted this literally, I'm sorry, half an hour ago. I posted this file called class PowerPoint. There's nothing really in it. It's just to help me keep pace. So what you should do is, if you don't have the PowerPoint printed out, don't worry about it. What you should be doing is today we're going to take a lot of notes. And we'll see how it goes. And if we'll, at the end of the lecture, I'll ask if people prefer this over the general PowerPoint, and we'll see what we prefer going forward. All right. Have your graphing calculator or any calculator handy. We're going to use it just a little bit today. Actually, we're going to use it a lot, but not in the same fashion as we did with correlation and regression. A little more just to do computations. Okay, so before I get started, anybody got any last final questions for me? I asked so I can take a sip of coffee. Okay. So, probability. So I want to start by recalling the definition of probability from your online lecture notes. So what we had was we're interested in finding the probability of some, what we call event E. Okay, so event E is what we're interested in. And we wrote it as this: the probability of event E. This is what you saw in the post lecture last week. So we're always going to read this as probability of event E. Okay, and it's just a real simple division problem. Okay, the most basic definition of this. So it's the number of ways E can occur. And then does anybody know what I divide it by? So it's a number of ways that this event E we're interested in can occur.
The sample?
Sample, you're thinking about like the sample space? Is that what you're thinking about?
Yes.
Yeah, it's the number of items in the sample space, or really just, you were dividing it by the total number of outcomes. Total number of possible outcomes. All right, so just like a real super simple example, okay? What's the probability you flip heads on a coin? Well, we all know this, right? Like we know it's 1/2. So, but this is how I'll write it. The probability you flip heads is equal to the number of ways you can flip heads divided by the total number of outcomes, or total number of possible flips. Well, the number of ways you can flip heads on a coin is just one way, right? Like you can only flip heads, just no other way to flip heads. And the total number of flips is there's 2, right? Okay. Kind of ring a bell, at least this definition from the post-class lectures last week? Okay, great. And just to make you guys laugh, I thought I'd share a little personal story for you here today. You guys notice usually the last 3 weeks I've been dragging quite a bit first thing in the morning, and I'm always like, I need coffee.
Yes.
My son slept through the night last night, 10 hours.
Whoa.
So I'm feeling great today.
Nice.
How old is he?
3 months.
He's gonna be a good sleeper. Don't worry.
I hope so. Because I need my sleep. My wife and I need our sleep. Anyways, I'm sure my son won't sleep. You know, I'm probably jinxing myself right now telling you all that, but it was just such a great night. All right, anyways, most of you are like, who cares, Matt? Let's get on with the lecture. So let's do that. Okay, so I really like this example here. I also, just as a hint, you know, your midterm is going to come up in a few weeks. So what I wanted to do is, this is a similar question I like to ask on the midterm, okay? So suppose you flip a coin and then roll a die. Okay, so you're going to do these 2 things in a row, all right? You're going to flip a coin, and then right after you get the result for the coin, you're going to roll a die. So you're going to record your results, okay? So the way I'm going to write my results is, could I flip heads and then roll a 3? Is that one possible outcome? Flip heads, then roll a 3?
No.
Yeah, if you're going to flip a coin and then roll a die, could you flip heads, right? The outcomes for a coin are heads, tails. And when you roll a die, and I should have specified this, we're only going to do 6-sided dice. You can get 1, 2, 3, 4, 5, and 6. So you absolutely can flip heads and then roll a 3. Does that make sense?
Yes.
Okay, what's another outcome that you could get?
Flip tails and then roll a 2.
Yep, tails, roll a 2, and you could keep going for these. All right. So the first question is this a probability experiment? Okay, and to be a probability experiment, it turns out this is. you need to meet two requirements, okay? The first is you need to have uncertain results, okay? Meaning, before I flip a coin and roll a die, do I know exactly what the outcome will be?
No.
No, I like to give this example. You know, I think I've said this in class. I used to live in Las Vegas. If I knew the outcomes of a die roll ahead of time, I would still be living there and I'd be very rich. Okay, so it's uncertain results. But then the other thing that needs to happen to be a probability experiment is it needs to be repeatable. Okay, meaning I can just redo this experiment over and over and over and over again, which I can, right? Like I can flip a coin and roll a die as many times as I want. All right, so the next question is, what is the sample space? And I denote the sample space by this funky looking S when I write it by hand. And it's a set, so it gets set notation, and it's just the list or set of all possible outcomes. All right, I'm just curious, does anybody know how many total possible outcomes there will be for this probability experiment?
Okay.
All right, so whenever you count something in mathematics and statistics, you want to count the number of total possible outcomes. There tends to be a multiplying effect, okay? How many outcomes are there when you flip a coin?
2.
How many outcomes are there when you roll a die?
6.
What's 2 times 6?
12.
Yeah, so what you're gonna see here is there should be 12 possible outcomes for this. And this is how I'm gonna write it. And you can see the pattern, right? You're gonna flip a coin, right? So the first thing you could do is get heads. Well, then you're gonna roll a die. You could get a 1. Well, I could flip heads, and then what's the next possible thing I could get on the die?
2.
Yeah, and then I could flip heads, then what else could I get?
3.
Yep, and you see the pattern. Head 4, head 5, head 6. So these are all the possible outcomes for this experiment where you flip heads first. But then what else could you do instead of flipping heads?
Tails.
Tails.
So you get tails, then a 1, tails, then a 2, tails, then a 3, tails, then a 4, tails, then a 5, tails, then a 6. So these are all the possible outcomes, okay? Generally on the midterm, I'll ask you a question where I'll say, hey, find the sample space. And it'll be something small where there's like 8 outcomes or 10 or 12 outcomes. For experiments where there's hundreds or thousands of outcomes, I won't ask you to find the sample space. Okay, so here's the next question, all right? What is the probability of getting a head or a 6? Okay, so I'm just gonna write this out using the definition real quick. It's the number of ways to get a head or a 6, and I'm always gonna divide it by the total number of outcomes. Okay. Well, let's start with the denominator, the bottom first. How many total outcomes are there for this experiment?
12.
Yep, so that's always the denominator. Boom, 12. Okay, so now you have to think logically here. Head or a 6. Is this outcome here, this H1, is this a head or a 6?
No.
So you got to think logically, okay? And this is, if I tell you, hey, I am a math teacher or I'm an English teacher, is that a true statement logically or is it a false statement logically? Am I a math or an English teacher?
It's true.
Yeah, it's true. I am. I'm one of those things. So whenever you see the or statement, only one of the things has to be true. So H1 is a head or a 6. Yes. Is H2 a head or a 6?
Yes.
H3?
Yes.
H4, H5, H6. Is T6, is that a head or a 6?
Yeah. Oh.
Yes. So it's 1, 2, 3, 4, 5, 6. The answer here is 7 out of 12. Okay. So listen, on your homework, and on the midterm, you don't even have to reduce this. Okay. You don't even have to write it as a decimal or anything. You can just leave it as a fraction. And if you get and I'm not big on simplifying fractions either. So if you have something like 6 over 12, you can leave it as 6 over 12, or you can write it as 1/2. I don't care. Okay, so what is the probability of flipping heads and a 6 now? So probability head and a 6. Okay. So it's the number of ways to get a head and a 6 divided by the total number of outcomes again. Okay, well, what's the denominator here always?
12.
Yeah, there's just 12 outcomes for this experiment. So now logically, the and statement works a little bit different than the or statement, all right? To have this be a true statement, both statements need to be true. Like something like this. I would say, I am a math teacher and a father. That's a true statement, okay? Because both of these are true. But if I say something like, I am a math teacher and an English teacher, that's not a true statement. So what is the only outcome that is both a head and a 6?
Each 6.
Yeah, there's no other argument here that's both a head and a 6. So this answer is just 1 out of 12. Okay. All right, remember these two probabilities here. Okay, these answers. Because what I'm going to do is I'm going to introduce later on in class as we go through the lecture some advanced formulas. And what we're going to do when I give the advanced formulas, I'm going to go back to this coin flip die roll example to prove that the formula works. All right, so all I want to do today is get through 4 formulas or 4 theorems in probability. And listen, I'll be honest with you, okay? The first few formulas, the next half an hour of class isn't the most interesting because it's just not, I'm sorry. But we need to get these basic concepts down. And then when the second half of class, I think we work some really, really interesting examples. So just bear with it if it seems a little boring. Okay. The first rule we want to learn today is what's called the complement rule, okay? And the complement rule goes like this. For any event E, okay, and its complement, which we denote as E with the superscript C, okay? So what a complement is in probability is it's all the things that could not happen, that are different from E. Like, let me give you an example before I finish this definition. If event E is roll a 6, can anybody tell me then what the complement of rolling a 6 is? What are all the other results on a die?
5.
2, 3, 4.
You could roll a 5. What else could you roll?
Oh, I mean, you have 5 different outcomes.
Yes. So the complement here would be to roll a 1, 2, 3, 4, or 5. So the complement is what's left over after that event. Okay. That's really what's going on here. Okay. So for any event E and its complement, E with the superscript, right? We have the following. If I ask you, hey, what is the probability of the complement happening? Well, it turns out it's just 1 minus the probability of the original event. All right. Or you can just do some simple algebra here. The probability of the original event is equal to 1 minus the probability of the complement. Okay. I'm just going to give a note here, and we're going to work 2 quick examples of this. Okay. This formula is super easy. And what I mean by super easy is after you see me do 1 or 2 examples, you'll be like, yeah, that's easy, okay? But often in probability, we use this rule when asked to compute a really difficult probability or really hard probability. So what you'll notice, and hopefully you guys will remember this, okay? Later on in class today, I'm gonna ask you, it'll be like the first problem I ask and everyone's like, oh, I don't get it. I'm gonna ask you a really, really hard question, all right? I'll say, hey, what is the probability of this? All right, and to find this right here, E, it's gonna be really hard, but actually finding its complement will be easier. So sometimes when I ask you to find the probability of an E, it's gonna be easier just to do 1 minus the probability of the complement, okay? All right, let me just run through 2 quick examples so you can see how to use this. All right, so according to AccuWeather, all right, has anybody ever heard of AccuWeather, the website AccuWeather? I'm just curious.
Yes.
Yeah. They're always wrong, but whatever. Okay, according to AccuWeather, the probability it rains today in Morristown, New Jersey, where I live, is 0.20, okay? All right, that's the probability it rains. So what's the probability it doesn't rain today in Morristown? Just real quick.
0.8.
Yeah, and so all you did here, that's incredibly obvious just looking at this, but it's just the complement rule. So event E here, what we're looking for is the probability it doesn't rain. The complement then, the opposite of it doesn't rain is it does rain. So then the probability it doesn't rain is equal to 1 minus the probability it does rain. Which is 1 minus 0.20, which gets you that 0.80. So you've all done the complement rule before, right? You've just never like maybe put a rule to it, okay? Does this make sense a little bit?
Yes.
Yeah.
Okay. Let's just do another one real quick.
Could you just go back to like 2 slides over? I missed one word. Okay. Thank you.
This right here?
Yeah.
Okay, yeah, I'll pause for some coffee. So even though I got great sleep last night, I still needed a pot of coffee. My wife was able to get off coffee. I don't know how she did it. Obviously, she's just a better person, but. No LOL there? Okay. All right, let's just do one more quick one of these. And just the die roll one. What's the probability you don't roll a 3 on a die? And again, on die, when I say die in this class, it'll always be a 6-sided die. So event E that I'm interested in is you don't roll a 3. Okay, so what's the complement of you don't roll a 3?
You do roll a 3.
Yeah. So the probability then that you don't roll 3 is equal to 1 minus the probability you do roll 3. So this is 1 minus, what's the probability you roll a 3 on a 6-sided die?
1 out of 6.
Yep. So you just change the 1 to 6 out of 6. And this answer is 5/6. Okay. So that's just the complement rule. Now, just remember, keep the complement rule in your mind for later on in class. Okay. Got to sneeze. Give me a second. Excuse me.
God bless you.
Thank you. Thank you. The allergies are killing me these days. Okay. Now we get our first advanced rule here, and it's called the general addition rule. And this general addition rule is going to be for 2 events. Okay. And the general addition rule goes like this. For any 2 events, okay, and we'll call those events event E and event F, okay? The probability that E or F occurs is given by. So if I ask you some question like, hey, what's the probability of event E or event F happening? Okay. Did I start class by asking a question like this? Actually?
Yes.
Yeah, I'm gonna quick go back in the slides. This right here, head or 6. So this is my event E and this is my event F, okay? So obviously the rule is called the addition rule. So here's the thing. In your mind, what you're gonna think is it's always addition, and then you're gonna pause, but sometimes subtraction as well. Okay, so it's gonna be the probability, you take the probability of the first event happening, E, then you add to it the probability the second event happens, F, always, always, always. And sometimes you're gonna subtract the probability of event E and F happening. All right, so it's always addition, sometimes subtraction. What I mean by sometimes subtraction, if events E, F are disjoint, okay, in disjoint, what that means is the events are mutually exclusive, meaning they cannot happen at the same time, so there's no overlap. So if the events are disjoint, then the probability of E and F is going to be equal to 0. Okay. So let me just prove that this formula works, okay? And then I'll do an example where I talk about events being disjoint versus not disjoint, and you can see the subtle difference. But I want to go back and using this formula here, okay? This formula, I want to get this same answer here. Okay, I want to get this 7/12, okay? All right, so does everybody have the formula copied? If you're taking notes.
Professor, I'm sorry. In the last F, where does the parentheses start?
Here. Is that what you're asking?
No, the one before the 0. Yeah.
Here?
No, down.
This one?
Where you put if events E F/F
Are disjoint. Then these parentheses.
Oh, that's a parenthesis. I'm sorry.
That's okay. Yeah. No, my chicken scratch is terrible here.
Sorry.
Yeah. It's one of the requirements in the job interview for being a professor. You have to prove they have bad handwriting. Okay. All right. So let's go back. And this was the question. All All right. You flip a coin and roll a die. Okay. The question was, what's the probability you get, oh my God, I even forgot the question. A head or a 6? All right, so you're gonna write it like this. The probability of a head or a 6. Okay.
About online classes.
You can go take a shit.
Yeah, exactly. Sorry.
I'm just gonna mute everybody real quick here.
Worst fear.
Just muting it. I just muted everybody. Got some background noise there. So just if you want to ask a question, turn your mic off. All right. So it's a probability of head or 6. It's okay. It's all right. You know, you guys will probably hear my kid crying in a little bit, so it's all good. This is probably of head or 6. This is the event E, and this is the event F. Okay. So just using the formula here, it's going to be the probability of the first event, which is head, plus the probability of the second event, which is roll a 6, and then minus this right here, E and F. So you're going to minus the probability of getting a head and a 6. All right, so remember, this formula should give us 7 out of 12, okay? Well, don't overthink this question. If you flip a coin, what's the probability you get heads?
Half.
Yep. If you roll a 6-sided die, what's the probability you roll a 6?
1 out of 6.
Yeah, okay. Minus, now look here, head, probability of a head and a 6. Well, I'm going to scroll back. We saw that the probability to roll a head and a 6 is equal to 1 out of 12. Okay, so you just need to do some common denominators here. The LCD is 12. So this is 6 out of 12 plus 2 out of 12 minus 1 out of 12. 6 plus 2 is 8. Wow, look at that. The formula works.
Give me 1 second to copy, Professor.
Yeah, of course.
I'm a little slow.
That's okay. That's okay. So sometimes it's hard to, how did you get 1/12? Let me go back just real quick. If you remember, this is how I started the class. I said, what's the probability of head or a 6? And then we did this probability right here, the probability of head and a 6, right? And we said the probability of head and a 6 is 1/12. It was like the second probability we did in class today. Does that make sense? That's okay. That's okay. Don't worry about it. Yeah, you're welcome. And so where I just saw, oh man, this head and the 6, I knew that this was 1/12 from earlier. Okay. All right, so do you notice how I said going back here, sometimes this is equal to 0, the events are disjoint. So I just want to show you an example where, real quickly, sometimes you add and these are disjoint, and sometimes you add and they're not disjoint.
I have a question real quick.
Sure.
How did you get at the bottom like 6 out of 12 plus 2 out of 12? I'm a little confused.
Sure. So it's just at least common denominators, right? So you look at 2, 6, and 12, and the LCD is 12. So to turn the 2 into a 12, you multiply by 6.
Got it. Okay.
Got it. Yep.
Oh, you got 6 on the top.
Yep. Boom. You got it. All right. Let's just do one more quick example here. All right. And this is about drawing cards from a deck of cards. From a standard deck of cards. Excuse me.
God bless you.
Ah, man,
Bless you.
the allergies are killing me. It's the worst. Okay, sorry. I mowed my lawn the other day, and my wife thinks it's because whenever I mow my lawn, I get sick. Okay. So I want to talk about a standard deck of cards before I do the probability. I just want to make sure we know what's in the standard deck of cards. How many total cards are there in a standard deck? Does anybody know?
52.
52.
Okay, yep. So there are 4 suits. What are the red suits?
Diamonds and hearts.
It's the suits I think about when I think about my wife. Aw. What are the black suits? Dad joke. It was a dad joke. Yeah.
Is that spades and clubs?
Yep. Thank you. Now there's 4 suits, right? The diamonds, the hearts, the spades, and the clubs. Now they all have the same exact cards in them. Okay, they all have the cards 2, 3, 4, 5, 6, 7, 8, 9, and a 10. Then they all have a jack, a queen, a king, and an ace. Okay. So there are like 4 jacks in the deck. There's 4 sevens in the deck, so on and so on and so on. So each suit has 13 cards. Okay, and 13 times 4 gets you that 52 that you guys, right. Okay, so here's the question that we're gonna do. Suppose you shuffle up a deck of cards and I say, hey, draw 1 card from the deck, okay? So, draw 1 card from the deck. So I got 2 questions for you here. 1, what's the probability of a king or queen? Okay, and I just want to use this formula here, all right? So what's the probability that you reach into this deck, you shuffle it up, and you get a king or a queen? So you're just going to write it like this. It's the probability of getting a king or a queen. So just using my formula, this is my event E, and this is my event F, okay? So I'm just going to straight up write this formula here. So it's the probability of a king plus the probability of a queen minus the probability that it's a king and queen, which seems weird, okay? So when you reach into a deck of cards, can anyone tell me what the probability you get a king is?
4 out of 52.
Yep, there's 4 kings in the deck. There's 52 total cards. Plus, what's the probability you get a queen?
4 out of 52.
Yep, 4 queens out of 52. Now, this is what I mean by events being disjoint, okay? Can you reach into a deck of cards, a standard deck, and look at the card and say, ha, it's both a king and a queen?
No.
No, you can't. So this is what I mean by disjoint. All right, these events cannot happen at the same time. So what is the probability you reach in and get a king and a queen?
0.
Yeah, 0 out of 52. So this would be 4 plus 4 gets me 8 out of 52, which if you wanted to simplify this, would be 2 out of 13. Okay. Now let me ask you a follow-up question, just so you can see. What's the probability of a queen or spade? So just going to use the formula here. Probability of a queen or a spade. Sorry about that typo there. So I see the or statement. So I'm always going to say it's the probability of the first event, queen, plus the probability of the second event, spade. And then I'm just going to write minus the probability of a queen and spade. All right, so how many queens are in a deck of cards?
4 out of 52.
Okay, how many spades are there?
13 out of 52.
Yep, look here. So now here's the thing why you have to be careful about the problem. If you just add these together, 4 plus 13, you get 17. You guys think the answer is right, that it's 17 out of 52?
No.
No.
What did I double count?
The spade queen.
Yeah, so I counted in the 4 queens, the queen of spades, and I also counted the queen of spades in here. So you have to subtract the probability that it's a queen and a spade. Well, the denominator is 52. How many cards in the deck are both a queen and a spade?
1.
Yep, the queen of spades, 1. So the correct answer here is 4 plus 13, 17 minus 1. It's 16 out of 52, or just 4 out of 13. So if you do the subtraction here, it just really depends on the problem. You have to think it through. Okay? So does that kind of make sense?
So wait, I have a quick question. How
Sure.
did you get the 1 out of 52?
This queen and a spade. So
But
you
I
have
thought
to,
you said it's disjointed, right? Wouldn't it be 0 out of 52 again?
so king and queen are disjoint because you cannot draw a card and have it be both a king and a queen. But you can draw a card that's both a queen and a spade, because if you look back here, there's a queen of spades.
Oh, okay.
That's why it's 1 out of 52.
Okay, thank you.
Make sense?
Yeah.
All right, so generally you just have to think through the problem. Okay, like can these happen at the same time, stuff like that. Okay. All right. Now we get into what I think are the more interesting problems, the much, much more interesting problems, okay? And to do this, we need to define types of events, okay? So 2 events are independent, so we call them independent events, if the occurrence of the first event E does not affect the occurrence of the second event F, okay? So what we're gonna be looking at, what this means by here is, we're going to be computing the probability that 2 or more events happen at the same time, okay? Or those outcomes, happen one right after the other, okay? So we're going to talk about first independent events. And then this is a little bit of a typo here. 2 events are dependent. Sorry about that. Didn't get a chance to proofread before I finished these slides. Okay, independent if the occurrence of the first event does not affect the occurrence of the second event F. And dependent events, 2 events are dependent if the occurrence of the first event E does affect the occurrence of the second event F. All right, we're going to spend most of our time talking today about independent events. So let me give you some examples of independent events, okay? Coin flip and die rolls are examples of independent events. Like that first example I started class with, when you flip a coin and then roll a die. If I flip heads, okay, will that change or impact the probability that I roll that 6? What do you guys think? If I flip heads on a coin, does it affect the probability that I'm gonna then roll a 6 on a die?
No.
No.
No. Okay, so that's an independent event, okay? Another example of this would be sampling or selecting with replacement. So for example, suppose I say, I want you to draw 2 cards from a deck of cards, one after the other, but after you draw the first card, you put it back in the deck, okay? So suppose I want you to figure out the probability you get 2 queens in a row. All right, so you shuffle up the deck. What's the probability you get the first queen from the deck?
4 out of 52.
Yep. If you put that queen back in the deck of cards, what's the probability you then draw another queen?
4 out of 52.
Yeah. So it's when you sample or select, but you put the object back, that's independent. Or the third one, which we'll use a lot today, is or in one example, excuse me, is sampling / selecting from a large population. All right, so what I mean by that is, suppose you want to sample people in the United States, and you want to sample 2 people in a row, and you want to figure out what's the probability you get 2 females in a row, okay? So there's 330 million people in the United States, roughly. So if you go into the population and the first person you select is a female and you take that female out of the population, is it going to change really at all the probability that you select another female?
No.
No, it's not. It's just not going to change the probability in any measurable way. So whenever there's a large population and you're taking people out of it, that's independent. Okay, dependent here, we probably won't get to in today's class. But this is when you do sampling, basically selecting without replacement. Or from a small population. So to go back with that deck of cards example, suppose you shuffle up a deck of cards and you draw 2 cards in a row, and you're going to take the first card but not put it back, okay? So you want to get 2 queens in a row. You shuffle up the deck. What's the probability you get a queen the first time?
4 out of 52.
Okay, now you take that queen and you leave it on the table. What's the probability you go back into the deck and get another queen?
3 out of
3 out of
51.
Yeah, 3 out of 51. So notice how the probability changed slightly. Okay, those are dependent events. All right, but this week with our lecture, we're going to focus on independent events. All right, let's take actually, we're going to take a real short break. We'll do a 5-minute break. Does that sound okay?
Yep.
All right, so we'll come back. Let's come back at, let's say 9:56-ish. Okay, I'm just going to go fill up my coffee and we'll start back up, okay? All right, everybody enjoy their break. All right, everybody. Can you all hear me again?
Yes.
Okay.
Yes.
Let's finish up for this morning. All right, so we have these two types of events, independent, dependent events. So we're going to focus primarily on independent events. So we're going to get to my favorite rule, right, for this class. It's called the general multiplication rule, and this is for independent events. Okay. So it just goes like this. For any two events, okay, and we'll call those events E and F, okay? We have, if I say, what is the probability that event E and event F happen? Okay. So notice how I started the class with two problems. So it's the probability that event that you roll heads or a 6. And then what was the next question I asked? The probability that you roll heads and a 6, right? So if the two events are independent, so for any two, and let me put that in here real quick, independent events. If I ask you what's the probability that both E and F happen, you're just going to take the first event E and you're going to multiply it by the probability of the second event F. That's it. Let me just do a quick example to show that this works, okay? So you're going to flip a coin and then you're going to roll a die. All right, what's the probability you flip heads and roll a 6? Okay, so it's the probability that you flip heads and roll 6. Did we do this problem already in class? Have we done it a bunch?
Yeah.
What should the answer be?
You 1 out of 12.
1 out of 12, okay? So we know the answer should be 1 out of 12. So let's verify that this formula works. The first thing I asked, to use this formula, you have to ask is flipping heads and rolling a 6 independent of each other? Meaning if I flip heads,
Yes.
yeah, they're totally independent. So you're just going to take the probability of the first event and you're going to multiply it by the probability of the second event. Well, when you flip a coin, what's probably you get heads?
F.
Yeah. What's the probability you roll a 6?
1/6.
Yep. What's 1/2 times 1/6? Just multiply across. So 1 times 1 is 1, 2 times 6. Wow, look at that. This works. Okay. So whenever they're independent and you see the and statement, and implies multiplication. Okay. Whenever you see the and statement, it tells you to multiply. All right. Whenever you see the or statement, it tells you to add, sometimes subtract. Okay. Be honest with you though, two events, kind of boring. Okay. So there's a continuation of this. For any number of independent events, E, F, G, H, doesn't matter if there's 4 or there's 100, okay, or there's 1,000, as long as all the events are independent. The probability that event E and event F and event G and event H and how many ever all happen, okay? As long as they are all independent, you just take the probability of the first one, E, multiply it by the probability of the second one, F, multiply it by the probability of the third one, G, and so on. This is where things get more interesting. Okay, so just remember, as long as it's independent, just multiply, multiply, multiply. All right. I think I have some fun examples for this picked out. Okay. Guys, okay if I move on to the fun examples now?
Yep.
Yes, please.
So the first example I have, I don't know why I like this one, but it's about a game you might have played as a child. It's called the game of Yahtzee. Has anybody ever heard of this game?
Yes.
Yeah.
Yes.
Okay. I know I've played Yahtzee before. I totally forgot how to play, but the whole idea of Yahtzee is you roll 5 dice and you record your result. So in the game of Yahtzee, there's actually something called rolling a Yahtzee. Okay, when you roll, this is the only thing I remember about the game. When you get this roll, you get to yell Yahtzee, and you win that round. Does anybody know what rolling a Yahtzee in the game of Yahtzee is?
All 5 numbers are the same.
Yep. Okay. So all 5 numbers match. Okay. So here I've got 2 questions for this. So if you roll 5 dice, what's the probability they are all the number 6? Okay, so you're just going to take 5 dice in your hand, you're going to throw them, and we want to compute the probability that you do this and all 5 dice come up to be the number 6. All right, so this is what I mean by, I think the first part of class, the examples were kind of like meh, but this one is just a little bit harder maybe perhaps, right? You guys think this one's a little bit harder? Maybe,
Yep.
maybe not. Okay. So when you get these harder ones, okay, like now I've got 5 dice and I want them all to be the number 6. Listen to how I say this. How you write the problem is incredibly important, okay? Because that tells you how to solve the problem. So the way, when I say how you write the problem, there's only 2 types of statements we know, okay? We know and statements and we know or statements, okay? So this is how I would tackle this problem, okay? So it's the probability that all 5 are the number 6. Okay. So to do this, the first die has to be a 6, okay? Would you agree? The first die that comes up has to be a 6?
Yes.
All right, what does the second die have to be?
6.
Same.
Okay, so if I want them all to be the number 6, would I write an or an and here? Between them.
And
Yeah. So the first needs to be a 6, and the second needs to be a 6. And what does the third die need to be?
6.
And what does the fourth die need to be?
6.
And what does the fifth die need to be?
6.
Yeah. Yeah, you guys got it, obviously. So do you notice how I just wrote this really, I'll pat myself on the back, smartly, if that's even a word. Yes, it is. But when you see the and statement, what mathematical operator does the and statement imply?
Multiplication, right?
Multiplication.
So next you have to ask yourself is, are these independent events? So if I roll a 6 on the first die, does that change or affect the probability I roll a 6 on the second die?
No.
No. And obviously you don't want to get like too meta on this problem and say, well, you know, if you throw them in your hand and they bump into each other, they affect, there's just no way to account for that. So yeah, just they're definitely independent. So you're just going to multiply. So it's probability the first die is a 6 times the probability second die is a 6 times probability the third is a 6. This is the only time I'm really going to write all these out. Probability of the fourth die is a 6 times the probability of the fifth die is a 6. All right, well, what is the probability of the first die you roll comes up as a 6?
1/6.
Yep. What's probably the second die is a 6?
1/6.
Yep. And the third is a 6. And the fourth is a 6. And the fifth is a 6. Boom, just like that. So this is 1/6 to the fifth power. So you just grab your trusty calculator here. 1 to the fifth power is 1. 6 to the fifth power, you type 6. And then this little caret sign here means raise to the fifth power. And you should get this, 776. So the probability that you roll 5 dice and they all come up as a 6, it's very, very small. You see how I tackled that?
Hey, Professor.
Yeah.
So why did you separate it? Like, why can't you just, do you want to keep it in fraction form like that?
I keep this one in fraction form just because it's simple like this. A lot of times if you were to do this in your calculator.
Yeah, it comes out as like scientific notation.
Yeah. Yeah, you'd have to move the decimal place to the left 4 spaces. That's why I just left it as fraction, because it was easier for me to consume and do. All right, let me just ask one more follow-up to this Yahtzee question, okay? So here's the next question, okay? You're gonna roll 5 dice. What's the probability they all match? Okay. So I have no idea how to do this problem. That's not true. I do, but I'm just asking, does anybody have a suggestion how you tackle this one?
Isn't it just the same as what we just did?
Roughly, but now here's the thing. What we just did was the probability they're all 6s, right? What's another way they can all match?
Any other number?
They can all be 5s. Or,
Oh, so you're actually doing that probability
Yeah.
times.
so you have to be
Okay.
careful. Listen to how I say this, okay, everybody? This is because how you write it is important. If I want all the numbers to match, all the numbers to be the same, they can all be 1s, correct?
Yes.
Or they could all be what?
2s,
Or,
3s.
Et cetera, et cetera.
yeah, so listen. So it's a probability they're all 1s, or they're all 2s, or they're all 3s, or they're all 4s, or they're all 5s, or they're all 6s. So when you see the or statement, what does that imply?
Addition.
Addition. And now here's the thing. You only do subtraction if they can happen at the same time. So in this case, none of them can happen at the same time because I can't roll all ones and at the same time have the dice be all twos. Like that doesn't make sense. So this is just the probability of all ones plus the probability of all twos plus the probability of all threes plus the probability of all fours plus probability that they're all fives plus probability that they're all sixes. So now we just have to figure out what all these are. Well, did we figure out the probability that they're all sixes already?
Yes.
Yes. So they'd all be the same as that.
Yeah, like you'd have the probability they're all ones would be the exact same as this. Like it makes no difference if it's a 1 or a 6 here. So yeah, you're absolutely right. So 1, 2, 3, 4, 5, 6. This is 6 out of 7, 7, 7, 6. Which simplifies to 1 in 1,296. So notice like the math here is, I honestly, I don't, and I hope I'm not wrong and I don't insult anybody here, but like, I don't think the math is hard. Like we're just multiplying fractions here. I think what's hard is how you set up the problem. Like as soon as you know how to set up the problem, like the math isn't necessarily hard. What's confusing is knowing exactly how to set it up. You guys agree?
Yes.
Yes.
Okay. Let's do another one. I got 2 more what I think are interesting examples here, okay? All right, I want to talk about so a few years ago I went to every year actually, but this happened a few years ago. I get a physical, right? Like I just go to my physician, I just get my annual physical, and usually it involves blood work, okay? So it's my least favorite part, okay? I got to go get a needle stuck in me and they test my blood for a bunch of different things. And one of the tests they do is this thing called the ELISA blood test. And what the blood test does is it detects antibodies in your blood. And what does the most common use of it is the most common use for this test is it's used to detect for HIV among other things. Okay, that's the most common use of this blood test. Okay, and so let me give you some statistics about this blood test. Okay, the blood test is what they call 99.5% effective at detecting antibodies in the blood. Okay, what this means when I say they're 99.5% effective is the probability that you take the test and it comes back correct is 0.995. Okay, is that a pretty good probability?
Yeah.
Okay. Then what's the probability the test comes back incorrect?
0.005.
Yep, just 1 minus this, okay, because that's the complement of it. It's incorrect. Just so we're clear, what incorrect means in this case is it means it's a false positive. Okay, so imagine you're taking this blood test to get detected for HIV, okay? All right, let's just go with that example, okay? What would be a false positive if you're taking this test for HIV?
That would mean that you tested positive for HIV antibodies, but you don't actually have
Yeah.
HIV.
So tested positive for HIV when you don't have HIV. Is that a good or bad outcome?
It's bad, but also better than the alternative, I guess.
Yes, it is a bad outcome. These drugs actually, they can measure false positives very easily, but what they can't measure is what's called false negatives. The reason drug manufacturers have a hard time testing for false negatives is because when you get a negative result, you just don't get tested again. You're just like, oh, I'm good, I'm negative, and I walk away. So it's really hard for them to estimate that. But false positives are easy for them to measure because we'll talk about why, okay? Okay, so I got 2 questions for this problem, okay? So everybody just remember this ELI SA, this blood, I'm just gonna call it the blood test. It's 0.9, the probability is correct is 0.995, the probability it's incorrect is 0.005, okay? If 5 people take the test, what's the probability all tests are correct? Okay, so we're just gonna have 5 people across the country take this test, okay? And I wanna compute the probability that all people, when they take the test comes back correct, okay? So you have to figure this out, okay? And the way you got to figure this out is you have to figure out how to write it, all right? How would you, can someone tell me how they might write it using some of the stuff I've talked about?
So you got to do like 5 individual. So like probability, first one correct,
Yep.
and then multiply it.
Hold on. First is correct. And if I want them all to be correct, what does the second one need to be?
Second correct.
Then you can see the pattern immediately. And the third needs to be correct. And the fourth needs to be correct. And the fifth needs to be correct. Okay? So the next thing you have to ask yourself is, okay, great, I see the and statement that implies multiplication, sweet. But I have to ask myself, are these independent events? So meaning, suppose I take this test. Does somebody at a different hospital who takes this test, will my results impact their results?
No, not with a large enough sample size, right?
Yeah, I mean, so like, even if there were only 5 people, right? Like even if they're all at different hospitals, like they're just, my test results are not going to impact someone else's. Even at the same hospital, they're probably not, my results would not impact someone's results, right? Like if they were all going to be incorrect, it would probably be an issue at the hospital itself, not like my test impacting theirs. So they're all independent. Okay, so it's just the probability the first is correct times the probability the second is correct. And you keep going times probably the fifth is correct. All right, well, what's the probability test comes back correct?
0.995.
0.995.
Yep, and but how many times are we multiplying this together?
You
5.
can put it to the 5th power.
Yeah, so then you just grab your trusty calculator here. It's 0.995 raised to the 5th power. So the answer is 0.975. I'll just go to 3 decimal places, 0.975. Pretty good odds, right?
Yes.
Yeah, that's great. Okay, let me just ask one last follow-up question with this. Still, it's actually just going to be example 2. It's continued. This is a very common test, okay? So actually, like anytime anybody gives blood, they run this test. You know, I just got a random physical. They run this test on my blood. So today in this country, okay, how many people do you think are going to get this blood test done? Is it a lot or a little?
A lot.
A lot. Thousands of people. Okay. Every time you go in for surgery and they take your blood, they're probably going to run this test. Okay. So let's just lowball it and say, if 1,000 people take this test, what's the probability of at least one incorrect test? So today, the probability of at least one false positive. All right. So the thing you have to check here, 1,000 people are going to take this test, and I want to find the probability at least one incorrect. I don't know. This seems really hard. Oof. I'm going to pause for coffee. So does this one seem different than any of the ones we've done before?
Not really. It's just using the incorrect or like the complement, I guess, of what we just did.
All right, so first off, 2 things. One, you stole my thunder, okay, by saying not really. That was a joke, by the way. But yeah, you're right. It just involves like maybe a complement rule here. Okay, so here's the thing. If 1,000 people are going to take a test, okay, what are the number of ways or the number of tests that can be incorrect? Okay, can 0 tests be incorrect?
Yeah.
Okay, out of the 1,000. Can 1 test be incorrect out of the 1,000?
Yeah.
Okay, that's at least 1, right? 1 test is incorrect. But even just find the probability of exactly 1 test in 1,000 being incorrect is really hard, because it's like, is it the first test that comes back incorrect? Is it the 5th? I don't know. 2 tests could come back incorrect. 3 tests could come back incorrect. 4 tests. There's a non-zero, there's a small but non-zero chance that all 1,000 tests come back incorrect. So at least 1 incorrect are all these options right here. So this is my event E then. This is at least 1. Well, what is the complement of E then? How many tests are incorrect?
0.
Yeah. So then this is really hard. So this would be 1 minus the probability that 0 are incorrect. Well, if 0 are incorrect, that means all the tests are what?
They're all correct.
Yeah. So this is 1 minus, if I want all tests to be correct, first is correct. And the second is correct. And all the way to the 1,000th test is correct. So you see the and, it implies multiplication. Okay. So this would be 1 minus, the probability that they're correct is 0.995. And how many tests do I want to be correct?
1,000 or, yeah, I guess 1,000.
Yep, raised to the 1,000th power. So let's grab our calculator and see what we get. So it's 1 minus 0.995 raised to the 1,000th power. Okay, so this is the probability that today, somebody's test is going to be incorrect. 0.9933. There's almost 100% chance that someone's test today is going to be incorrect. So what I'm telling you is today, someone who takes this test is going to test positive for HIV when they do not have HIV. Okay, it's almost guaranteed that it's going to happen today. Is that a good thing or bad thing?
Bad.
Yeah, but it's going to happen today. So what do you think happens when someone's test comes back positive?
They retest.
Yeah, they test again and again and again and again because they know that this is likely to happen, or it's going to happen in the aggregate. All right, so here's one thing I want to talk to you about. Whenever you see this type of question, at least one, you're going to use the complement rule. Okay. I know I went through this one really quick, but does it kind of make sense?
Yes.
Okay. Let me just do one more of these questions, okay? And I have another like kind of macabre example, I'm sorry. I came across this problem a while ago. I found it really, really interesting. And this problem is about the Challenger disaster. Okay, how many people know the Challenger disaster when I say that?
Me.
What is the Challenger disaster?
It was a space shuttle.
Yeah, so the space shuttle, they say it exploded, but that's not really what happened. I'll talk about it. So the space shuttle loss occurred, I believe it occurred on 1/28, according to my notes, 1986. It was a national tragedy. So the reason it's so big of a deal is the Challenger space shuttle had a grade school teacher on it, and it was a big educational thing. So what they had was they were going to put a teacher in space with the astronauts, and she was going to do like lessons about space to students. And so like the country was watching live when this happened. Okay. And so imagine the entire country's watching live, and then the space shuttle shoots up and people think it exploded, but that's not exactly what happened. So what happened was an exterior fuel line caught fire, and the space shuttle actually got engulfed in flames. Okay, so it was real bad. Okay, so here's what I want us to do. I want us to let's compute the probability of a shuttle loss. Okay, so I want us to compute a probability that NASA probably actually computed for the astronauts before they went into space. Okay, so they probably said, look, you're gonna go into space in the space shuttle. This is the probability that your space shuttle will be a loss. Okay, so to be able to answer this, I have to give you some pieces of information. Okay, so all items on the shuttle are classified by what they call criticality. Like literally every item that goes on the shuttle gets a criticality score, okay? Like bolts, everything, okay? So criticalities go like this. There's criticality 1, criticality 2, criticality 3, criticality 4. So the items that are the most important are the criticality 1 items. Okay, let me give you an example of something that's not a criticality 1 item. The seat belt for one of the astronauts, okay? If the seat belt fails, okay, will the shuttle still probably make it home?
Yeah.
Okay, yeah. So the seatbelt probably is like criticality 4, criticality 5, whatever. Criticality 1 items are specified as the following. If a crit, I'm just going to call it crit 1 item fails, the shuttle will be a loss. Okay, so if this item fails, the shuttle will not make it home. Okay, let me give you an example of the criticality 1 item. The wings, okay? The wings are criticality 1 item, okay? If the wings fall off the space shuttle, it's not making it home. The other important thing about it is there's no backup for these items. Okay, so like there's no extra set of wings, okay? And the other thing about criticality 1 items is they have to work independently of each other. And NASA certifies that the probability that these items work prior to launch, they have to work 99.99% of the time. Okay, that's what they say they work. So what happened with the Space Shuttle Challenger is, I think it was like an exterior fuel tank, exploded, and it caused liquid oxygen and hydrogen to mix and form a fireball that engulfed the shuttle. So that exterior fuel tank was a criticality 1 item, okay? So my question for you is this. If you're gonna go into a space shuttle, do you want a lot or little criticality 1 items?
Little.
You want as few as you can have, okay? I'm just curious, can anybody ballpark how many criticality 1 items there are on a space shuttle? I mean, we don't have the space shuttles anymore, and SpaceX launches us into space now, but
Probably a lot.
a lot, okay. I don't know, what's a lot? Is 10 a lot? Is 100 a lot?
Probably more than we'd be comfortable with. Criticality 1 items like wings and like exterior stuff that if it disappeared, they would crash.
I agree. Okay, so then actually, I'll tell you guys the number of criticality 1 items on the Space Shuttle Challenger. There were 748 of them. Does that seem like a lot?
Yeah.
Yeah.
Yeah, okay. So knowing this, there's 748 of them. They work independently, but they do work 99.9% of the time, okay? So let's now compute, knowing that, the probability of a shuttle loss. Okay, so to go back here, all it takes for the shuttle to be a loss is 1 criticality item fails. Okay, that's all it takes. Okay. Well, if 2 criticality 1 items fail, is it still a loss?
Yeah.
If 3 fail?
Yep.
Yep. So all it takes is at least 1 to fail. That's it. So it's the probability at least 1 crit item fails. Okay. All right, so you can see how this problem is set up kind of like the previous one. What's the keyword that tells me how to, or keywords that tell me how to solve this?
At least 1.
At least 1, yeah. So we have to do the complement of this. What is the complement of at least 1 fails? Well, at
That
least,
none fail.
that's right. So it's 1 minus the probability that none fail. Or 1 minus the probability they all work. Well, do I know the probability that they work?
Yes.
Okay. So I told you that criticality 1 items have to all work independently of each other too. So it's probably the first works. And the second works. And all the way to the 748th works. Well, this is 1 minus the probability that they work is 0.9999. And how many of them are there?
748.
So you just raised to the 748th power. So this would be 1 minus 0.9999 raised to the 748th power. So the probability that this shuttle was going to be a loss even before it took off was 0.072. So it was a little over 7%. So my question is, would you be comfortable getting on that shuttle?
Nope.
I would not. No way. That's like, imagine if air travel was like that. Air travel's like, well, you know, there's a 7% chance you're not going to make it. I would never get on an airplane. So anyway, I just found this incredibly interesting because these astronauts were probably told this beforehand. Like NASA definitely computed this probability. And they said, hey, look, guys, you know what? There's a 7.2% chance, you know, the shuttle will not return home. They were brave people for doing it. All right. At least were the last two examples a little bit more interesting? The blood
Yes.
test and the space shuttle one?
Yeah.
Yeah, I mean, I think so. All right, let me just real quick, I just want to do one last problem, one last theorem, and I'm going to have to burn through this real quick. This is called conditional probability. And it's for two events, E and F, okay? It's computing the probability when you're given an extra piece of information, okay? Let me explain that. Suppose you roll a 6-sided die, okay? So as soon as you roll the die, I cover it up, okay? What's the probability that you just rolled a 3?
1/6.
Okay, but suppose that I look at the die and I say, hey, guess what? You just rolled an odd number. Now what's the probability you rolled a 3?
0. Oh, sorry. 3 out of 6.
Not 3 out of 6. You're close with the 3. How many odd numbers are there on the die?
3.
There's 3. So there's the numbers 1, 3, and 5. So if I say, hey, you just rolled an odd number, the probability you rolled a 3 would now be 1 out of 3. Okay, because you're getting an extra piece of information. So let me just show you the formula and work through the example here. So for any two events, E and F, if I say the probability of event F given event E, so this sign here means you're given some information, okay? This is just going to always be equal to the probability that E and F can occur divided by the probability of E, or the number of ways E and F can occur divided by the number of ways E can occur. All right, so let me just keep this formula handy. So let me just do this one quick example with it here. What's the probability you roll a 3 given you rolled odd? All right. So just using this formula, it's the probability that you roll a 3 given that you rolled an odd number. Okay, so I'm telling you that you rolled odd, okay? So just going back here, it's the probability of the two events combined. So it's the probability you roll odd and roll 3 divided by this second probability here, the probability you roll odd. Okay, well, the probability that you roll an odd number and a 3 is just 1 out of 6, right? There's only one way you can roll on a die that is both odd and 3. It's that you roll a 3. And then the probability that you roll odd is 3 out of 6. So when you have a fraction divided by a fraction, you keep the top, change to multiplication, and flip. So this is just 1 times 6 is 6. Out of 6 times 3 is 18, which is that 1/3, as I said you would get. All right, the way I just want to get to the homework problem that you're going to have. Let me find it. Where are you? Okay. And this, I'm just going to burn through in 9 minutes, okay? And this is our last example of the class. Okay, and this is about, have you guys heard about this Titanic voyage?
Yes.
Okay. You know, Kate and Leo. Leo didn't make it, but Kate did. No LOL there. Okay. So it turns out that I have some passenger data on the Titanic, okay, that I want to share with you. Okay, so these are the actual numbers from the Titanic, okay? Did some people survive the Titanic?
Yeah.
Yes.
Yeah, okay, and some people died. So here's what I have. I have data on passengers who survived and passengers who died on the Titanic. And I have it broken down by if they were male, if they were female, or if they were a child. Child is not broken out by sex, it's just if they were a child, okay? All right, so let me give you the number of people who survived. All right, there were 338 males on the Titanic who survived. There were 316 females on the Titanic who survived. And there were 57 children on the Titanic who survived, okay? So if you add all these up, there were 711 people on the Titanic who survived, okay? Now, unfortunately, let me give you the sad part, the people who died, okay? There were 52 children on the Titanic who died. There were 109 females on the Titanic who died. And then there were 1,352 males on the Titanic who died. Okay, so the number of people who died on the Titanic is 1,513. The number of males on the Titanic were 1,690. The number of females on the Titanic were 425. And the number of children on the Titanic were 109, just adding down. And there were a total of this many people on the Titanic, 2,224. Okay? Everybody got that real quick? Is it just real quick before I go on? Is anybody surprised by these numbers at all?
A lot of people that died.
A lot of people that died. Yeah. Okay. So here's what I'm going to do. Imagine you have a list of all the passengers, okay? You're going to select a passenger at random. Okay, you're just going to shuffle up. Imagine you have all the names in a hat. You're just going to select a passenger at random. Okay. First probability I want to find is, what's the probability they survived? Okay, so the probability just any passenger survived the Titanic. Okay. Well, to do this problem, it's pretty easy. How many total passengers are there?
2,224.
All right, so that's going to be the number of ways you could select people. Going back, how many people survived the Titanic?
711.
Mm-hmm. So if you plug this in your calculator, you get roughly 42% of people survived the Titanic. Okay. Which isn't bad, you know, it's not great, not the worst. Okay. So here's the next question. If a female is selected.
I'm getting 32.
Is it 32?
Yep.
Let me see. $7.11 divided by, yep, you're right. 32, sorry, yeah, it's obviously 32. Okay, I did that on purpose to see who was paying attention. Okay, well done.
Got me.
Everybody else, terrible. Okay, real quick. So if a female is selected, okay, what's the probability they survive? All right, am I giving you a piece of information here now?
Yes.
What am I giving you? What am I telling you to start at?
Female.
Yes, so what I'm giving you here, going back to this formula here, I'm legit giving you that they're a female. I'm giving you the E. I'm telling you given that they're a female. So it's the probability they survived given that they were female. Okay? So just using this formula here, it's the probability or the number of ways both can happen. So it's the number of females and survived divided by the second part here, the number of females. So looking back, the number of females who survived is this number right here. And then total number of females is 425. So this is just 316 divided by 425. And hopefully I did this right. So if you were a female on the Titanic, there's a 74% chance that you survived. Okay, this is why Kate made it, okay? Now, last question for today. If a male is selected, what's the probability they survive? So what piece of information am I giving you?
Or male.
Yeah, so I want to find the probability they survived given that they were male. So it's the number of males and survived divided by the total number of males. So going back, here are the number of males who survived. Here's the total number of males. So it's 338 divided by that 1690. Rounding to 2 decimal places, you get 0.20. So this is why Leo didn't make it. All right, I know I'm butting up right against the end of the class, so my apologies. But you now have, I'll post the recording for this real quick. And let me just stop the recording.